Same concept behind Bernoulli's principle, which we'll talk about here in a minute. What this means is that as I go around the bend of the river, everybody's staying in line. Now, this is where you have to take yourself out of what we normally think of as speed and literally think about the issue here. What is speed? How do you determine speed? Time is part of it. Time and what? Distance. It's the distance traveled in a given amount of time, correct? Okay. Now put yourself in a relative point of view. This is where I really need you guys to be open-minded and really think about this. Going around a bend. If everybody, let's say it takes me 5 seconds to go around that bend, at the end of the 5 seconds, everybody has to be back in the line, correct? So the time is constant for everybody in there. You all have to be at the same spot in 5 seconds. What about the person on the inside versus the person on the outside? Who has a much longer distance to travel? The guy on the outside. Think about it. He's got a much larger arc to go rather than the guy inside the line. Does that make sense? Exactly. The guy on the outside has a much farther distance to run. You always want the inside track. Now, this is really important. If they're traveling at the same time, it takes the same amount of time. This guy travels a shorter distance in 5 seconds. This guy travels a much longer distance in 5 seconds. Who's traveling faster? The guy on the outside. Definitely, if you're arriving at the same amount of time, the guy on the outside is traveling much faster. Perfect example of that. Again, if you don't believe me on this, on your way home from school today, stop by the park. Get on the little merry-go-round. Have somebody push you while you sit in the middle. Then, stop it, move to the outside and have somebody push you. Why would you sit on the outside? Yeah, it's the same concept. It's a triple force. You have a much farther distance to travel in the same amount of time. Therefore, you're traveling at a much faster speed. It's the same concept. As you go around that corner, the outside's traveling at a much faster velocity than the inside. Yes. Because what we said yesterday, if you increase velocity, you increase carrying capacity. Remember we talking about that?
So the inside doesn't have as much carrying capacity. That's why the sand dunes on the inside.
Well done, Maitland. As you go around the bend, the outside's traveling at a much faster rate. Therefore, its relative carrying capacity increases, so do your roads at the bank.
That's why the sand slopes.
On the inside of the curve, we lose our velocity, and therefore we lose our carrying capacity, and therefore all those sediments that were held in suspension drop out of suspension. Does that make sense? Okay, water has a lot of blank spaces right there. Okay, good. Maitland gets it. All right.
It's just like the mirror.
It really is. Now, what's really interesting, if you take even a closer look at this image, really take a closer look at it. Rivers are not constant. If you watch Pocahontas, you'll learn that. Okay. Rivers are not constant at all. They're constantly changing. Take a look at the image. Really close look at the image. What do you see? Ground levels. The point bar is migrating. It's moving. The original river channel used to be here. But as it kept going around the bend, what was happening with the sand? Getting positive. But as it gets deposited here, what's it doing to the outside? Eating away at the bank. So as it keeps going around, this river is actually migrating that direction. And so what really happens here is you can start seeing this. This again is migrating in this direction. And so eventually what we get to is you get rivers that start doing this. You get these really, really tight meanders. Okay. Some of you guys might know this by a different name, which is switchbacks.
So like the Amazon River.
The Amazon has a lot. I'm thinking more like the Shenandoah River has a series of these. Okay. Now, from here, something even more interesting happens. Again, what's happening every time I go around the bend on the outside? It's eroding, right? How many of you guys ever swam in a river? Where are the best places to go swimming in the river? On the outside. Yeah. You ever notice that? It's always deeper on the outside of the bend.
Like the sand slopes down.
Exactly. This is why. Because as that comes around, if you want to look at it from a side profile, as that comes around, not only is it digging in, but then it starts to actually force the bank, forces that water downward. And so it actually literally digs out a trench on the outside of the turf.
I noticed, like, in my old science classes, we were, like, taking water, like, in a water bottle and, like, shaking it up and putting stuff in it. And, like, if you look at it, like, the particles on the inside of the spiral aren't moving as fast as the ones on the outside.
Exactly. Same concept. You know, you got much farther distance to travel, same amount of time. Fluid dynamics. Everybody has to stay together. Okay? Remember I told you guys that this has to do with Bernoulli's principle? You guys ever heard of Bernoulli at all? Yeah, probably not. You guys ever looked at a side profile of an airplane's wing? Where's the curved edge? Nope.
The tip of the wing.
It's on the top, and it's always on the front. The curved edge of the wing is always on top, and it's always in the front. Then it slopes down to the back. The bottom side is flat. Now let's talk about why. If the wind, this air is really a fluid, all these pieces have to be at the same line together. Remember, they move as a line. That means that at the end of 2 seconds, whatever time it takes, all of these must be at the same point in the same amount of time. Well, which group traveled farther? The ones on top. So air on top moves faster than air on the bottom. Okay? This is really cool. Go home tonight. Take a straw. Take a note card. Fill it up. Place it on the table. And then take your straw and pull it to the center. I'm serious. Try it. I think you'll be amazed what happens. Anyways, the whole concept here is that the faster air is moving, the less pressure it exerts. So the faster air is moving, the less pressure that it exerts. Which means, since I have a faster moving air on the top, my pressure pushing down is much less than my pressure pushing up, and that's how we get lift.
Wait, how would that be lifted up?
Because the air on the bottom is moving slower than the air on the top, so therefore the air on the bottom pushing up on the wing is giving more force up than it is getting force down, and therefore it's slowly, actually that's what gives lift to the plane. If you had a flat wing, the plane would never be able to leave the ground, ever. You need to have a curved wing, because it'll make the top air move faster than the air underneath.
I thought that, well, like, whenever I, like, stick out my hand and do the dolphin thing,
Yeah.
like, whenever you, like, raise it up, though, like, it's that it has to go, like,
Yeah, that's the whole point of your flaps. That's what they initially get you off the ground. But what keeps you up in the air is this concept of the curved wing. And that's called Bernoulli's principle.
Does that have to do with, like, fans and how the blades
I don't understand why it wouldn't be the bottom one that you have to go faster.
Okay, hear me on this one more time. The faster air is moving, the less pressure it exerts. Okay? worry about the reason why at this point. That's all you need to know. The faster air is moving, the less pressure it exerts. So since I have faster air moving on top of the wing, it exerts less pressure than the slower air underneath the wing.
What about
And therefore we get lift.
like the
So
pressure
don't ask
washer?
why it goes the pressure.
We don't need to worry about why that concept works. That is the main concept.
What about with like
This class isn't for that part. That's a physics class. Okay.
pressure washer?
Yeah.
It's just a lot of pressure.
Water.
Water.
You know.
How's it like in like a pipe air
The pressure you think about with a pressure washer is because of the slot that you have in the water pressure, or sorry, in the pressure washer. Again, same concept. You have water in is equal water out, so the water coming out is moving at a much faster rate. Now, when we're talking about exerting pressure, we're not talking about getting hit by it. Okay, that's when you think about pressure washer. That's what it's literally. Pressure isn't against; it's actually down at it. It's like getting hit head on. We're talking about this. We're talking about literally the pushing down of the air. Okay? So if you have a very slow moving water, it's going to exert more pressure on the outside of the channel than if you have rapid moving water. Okay? Yes.
When I was younger, like I had grass on my foot, and I like grabbed the.
Hold on. Are you sure this applies?
Yes, it does. Yes, okay. And like I thought I could just pick up the hose and like wash it off, but like it had like a power hose. It was like a power washer hose, and like I went to spray the grass off my foot, and it left the biggest welt because it came out so fast, and I had no idea why. Because it was going faster.
Okay.
Angel, don't.
Guys, if we look at this image again, we see the same point bar deposition. By the way, on your test, you'll be asked to explain how point bar depositions are formed. Remember, we talked about that. As you go around the curve, the outside moves faster, it increases carrying capacity and erodes at the outside. The inside moves slower, it loses its carrying capacity and deposits the sand. That's how point bars are created. You'll need to know that for your test. It is one of your essays. So you need to make sure you know that. Now, when we look at this next image, again, we see our point bars. And again, where do you see the point bars? Every single time. Where are all of our point bars located? If I'm going around a meander, again, a meander is our term for a turn.
Obviously, all the white spots.
Okay, but where? Is it on the inside or the outside of the turn?
What do you mean?
Always on the inside of the turn. So the point bars are always located on the inside of the curve. Now, my next question, what's going to happen there? Just remember, what's that water doing on the outside of the curve?
Eroding it.
It's eroding it.
It's
So-
eventually
It's eventually going to break through. When we get that, do you guys see anywhere on your map from yesterday where it has definitely broken through? Because look at your map. What letter represents something similar to what we're about to see here? C. Okay? That's what we call oxbows.
Would be the bar.
These are the point bar depositions. C is your oxbow. An oxbow is created when the meanders have basically completely been cut off. Brandon.
Can I show this? It says C with circles, but